So, as Zoltan said, I'll speak about OPM first and then OPM flow in particular second. So, about OPM, I'm going to try to answer a few very simple questions: who, why, what, and how. And I'll try not to go into much detail on this. However, on OPM flow, I will go into quite a bit of detail, since that is the main pilot for us in this project. So, Open Porous Media, the Open Porous Media initiative was started in 2009, and since then, various components and parts have been developed by various parties here. Oh, I see it's an important thing missing is we now also have TNO, the research institute from the Netherlands, should be one of the research institutes contributing. But Statoil has and still is a big contributor. Total has contributed. SINTEF, where I'm from, IRIS, TNO, University of Stuttgart, NTNU, and also various consultants have contributed to this software. Have come from industry and also from the public. Public funding is from the Research Council of Norway and from the EU through this project. And I'll just say that open source allows easier collaboration between different types of entities and organizations, such as companies, universities, research institutes, and also between different countries. There's much less need for ironclad contracts guaranteeing everybody their rights in a way that everybody is happy with, which is always very difficult to find in non-open source projects. So why OPM? So one very simple way to put it was that we had done a lot of work on advanced grids and discretizations at SINTEF. At the University of Stuttgart, they had been doing advanced fluid models through first UG, MUFTE UG, and DUMUX. And Statoil had a lot of industrial know-how and were willing to fund work to put these things together, to make things happen. Our vision used to be, and still is, to have a long-lasting, efficient, and well-maintained open-source software for flow and transport in porous media. So, and our ambition is to be a strong base for both industrial development and academic research. So, we're trying to go from this picture below, which is kind of an exaggeration of the way it was before, where industrial companies get their software from software providers like Schlumberger, others, and these companies again have research contracts with research institutes and other research communities, and it takes a long time for new things from research to make its way through the providers into the software and then into the industry. And the direct connection between the industry and the research community was, I think, not, I am exaggerating a little bit, but it was certainly not direct, in the sense that only very limited scope software and methods were actually directly taken from the research community and into industry companies. So with OPM, we want to have something more like this, and I think we are succeeding, where there's a tight and direct connection between industry and researchers. Because we collaborate on a project, we collaborate on the software with people both in industry and in the research community, actually committing to the same repositories and collaborating very directly. So why take OPM into this MSO4SC project? So one point is that we need to take OPM to where the usage is going to be. The cloud, large ensembles, larger scales. This is happening, and we need to be there. Otherwise, we will get obsolete. And another point which is very important to me is to have improved visibility and dissemination. We want to get more users, to get more feedback, to get more contributors, and also from SINTEF's point of view, to gain new clients for our research services. And for that, visibility of what we do is important. And finally, to improve the OPM software itself, as a goal in itself, to improve its deployability, usability, and scalability. So, what is OPM? First of all, it's a set of software packages written in C++. There's a reservoir simulator flow and a visualization tool which is specialized for reservoir data called ResInsight. And I'll demonstrate these two later, so I won't go into much detail about those. There are upscaling tools for physical properties. I'll talk a little bit more about the upscaling tools. And pretty new, there's a so-called flow diagnostic tools. Flow diagnostic tools are not simulators. They are cheaper, easier, faster to run than simulators, require a lot less resources, compute simplified properties, but can still give you quite a bit of insight into a case or a field. And also there's a toolbox. You can say that OPM as a framework is a toolbox with components for a wide range of porous media flow. So, but also very important is that we have open data, which in most research communities would be considered very important to have, and there would be good data sets available. But in reservoir simulation, I would say that that's not the rule, that data sets are openly available. Most data sets are closely guarded secrets of the companies that produce them at great cost. It takes a lot of money to do seismic surveys, and there's a long process from sensors and seismic surveys to a model that you can use for simulation. And they are therefore considered very valuable and usually not shared with the public or even researchers. It can be very hard to get access even for research purposes. But there is one full real field case made available by Statoil, the Norne case, and I'll tell you a little bit more about that. We also have some of the benchmark cases that do exist from Society of Petroleum Engineers Comparative Solutions project available, and quite a few testing data sets for OPM software. So, and all of these data sets are made available under an open license, so that anyone can use them, change them, and benchmark their own software against using them. So I was going to say a little bit more about upscaling, since that doesn't get its own talk. So upscaling is about finding effective coarse scale parameters. I don't know, do I have a pointer, Sultan, somewhere? Oh, I have this one, the built-in. So, so if this is a fine scale part of a model, and the resolution of this model is too high for you to simulate it in a reasonable amount of time, you want a resolution more like this. Of course, this is just an exaggerated figure. But then you need to compute upscaled properties for each of these coarse blocks. So this coarse block corresponds to these fine blocks. You take out this block, it looks like this. You compute an upscaled property, which is an effective property to use for simulation. Oh, thank you. It's need to, It says it thinks it's a keyboard.
Just close it and just use a pointer.
Yeah, it works. And what's the laser part? This one? No.
The top button.
Yeah, there's. Thank you. Okay, so for some properties, this is very easy. For example, porosity. The upscaled or effective value of a porosity is simply the average porosity. So you get a single value. So this is an example of upscaling porosity. But for other values like permeability, it's not so simple. For example, even if the permeability is a scalar value in this fine grid, the upscale values, it's going to be a tensor valued permeability. So that's due to layering, for example, and the grids being heterogeneous. So these are typical grids. This is slightly exaggerated in the z direction here, model of a domain that we want to upscale properties for. So and this is a typical grid for an upscaling. And this is a zoomed in on a part of this grid here. You see there are parts that are layers that are eroded out, and the layers are going up and down and so on. So it's and this is a typical case, not a particularly bad one. There are bad ones, but this is not bad. So for such cases, simple averaging is insufficient, and you must do flow-based upscaling. So flow-based upscaling means that you solve a flow problem, and then from the solution to that flow problem, you recover the effective properties. So, okay, I'll say a little bit about the Norne dataset. And it's the only publicly available real oil field dataset. It's a Norwegian sea oil field, so it's outside the north of Norway, or the middle of Norway, mostly. A very nice thing is that it includes historical production rates and measurements, so you can actually try to do better in terms of simulating it than those who have come before you. You can simulate it, you can run the simulation case with flow, you can run it with commercial software, but you're also free to try to do better than either of these tools, because the measurements are in there. Oops. It's not very large, 45,000 cells, but it has quite a few interesting features. I'll mention just a few. It has faults. You see, this is the part of the simulation grid. You can see that these cells here are connected, but then the layers split apart like this, so they are not connected. Or rather, some layers here are connected to different layers over here, geologically. So flow in this domain is constrained and controlled by the faults to a large extent. It's got a fairly high level of heterogeneity, and the properties are far from uniform. It's anisotropic. It has lots of ill-shaped cells, so if you're expecting cells to have nice shapes, this has some horrible cell shapes. Oh, sorry, I'm missing it. And it has some more or less horizontal wells, which has its own challenges related to how it connects parts of the reservoir that would otherwise not be that tightly connected, and also because it means it challenges you in how you model the wells. So finally, how? We do all our development in the open on GitHub using the pull request approach. So basically, this is yesterday's list of pull requests in one of the repositories. I see it's far too small for you to actually see it, but and then there's this is just an example of when you open such a pull request in GitHub and see what it looks like. This is pull request number 1186, faster ILU implementation. So which is made by a researcher at Atgeirr in Bergen in Norway, and then people from Germany and Norway have commented on it, and yeah, So it's so we comment on each other's pull requests, review them, look at them, discuss them, and when we're satisfied with, we merge them into the whole. We do continuous integration using a Jenkins server. So this is this here is from the GitHub discussion. You can, or if you are a maintainer, you can write Jenkins build this please into the discussion field, and the Jenkins server will get the message and build it and test it. So this is a very nice feature to have for a pull request. That means that every pull request can easily be tested, and there are some more things we can do with this that I don't show. We do regular releases every 6 months. The 2017-04 release is the current one. For collaboration, we have almost weekly hangouts between mostly SINTEF, Iris, Statoil, and some others to make everyone work towards the same goal. And it's very important that we avoid duplicate work by discussing who does what, because not everybody working on OPM is sitting in a single office or single building or single city or single country, but we are distributed. So coordination is a challenge, and we have found that rapid video meetings are very important for this. It's well worth the time. So for communication externally with users and get in touch with other developers, we have a website, mailing list, and we use the GitHub issues feature to get feedback about bugs and things like that. So that was all about OPM. Thank you.